Okay, so now we understand the principle of Gaussian elimination, i.e. with forward elimination and back substitution. We're going to start talking about some tweaks which we can make to the algorithm to either make things a little bit more friendly or reduce errors or perhaps even make it more efficient to do. Now the first of those techniques we're going to look at is something called partial pivoting. Now partial pivoting is a very simple idea, but it helps to reduce rounding errors because it reduces the chance of you having to add or subtract either really small numbers or really big numbers, okay? And we're going to look at an example of partial pivoting with exactly the same system of linear equations that we have just done, okay? But before we do that, I want you just to consider, by pausing the video for a couple of seconds, does the order of this equation here, this list system of linear equations, the way I've written it down here, does the order matter? So in other words, does the first equation, second equation, third equation, do I have to write them in that order? Okay, so hopefully you've paused the video for a couple of seconds and you've thought about the idea for yourself. And hopefully you've come to the conclusion that no, it doesn't matter. I mean, obviously we've established that we need to make sure that all of the x1s, x2s and x3s match up in their respective column. But the actual order in which I write down each equation doesn't necessarily matter. I.e. if I swap the first and second equation around, it's not going to change the values of x1, x2 and x3. Okay? So I'm going to use that principle here when it comes to partial pivoting. So let me write down the matrix which I want to try and solve through Gaussian elimination. So I'll take 2, 2, 2, 1, 3, 4, and 4, 3, 6. So that's exactly the same matrix as before. And I'll put my known values on the right-hand side. Again, remember, you don't have to put this vertical line in. I just do, just for the sake of illustration, to show this is my coefficients and these are my known values, but you don't have to do that. Okay, so partial pivoting follows exactly the same process as naive Gaussian elimination, except I follow this idea of, well, hang on a minute, the order which these rows come in doesn't necessarily matter at this stage. So what I'm going to do first of all is I'm going to choose the maximum value out of all of the first column because that's what I'm going to go for first. I'm going to try and eliminate x1, okay? So I'm going to choose the maximum value out of 2, 1 and 4. Now if you have negatives in there, just choose the absolute values, the maximum of the absolute values, okay? But in this case we find that the maximum is 4, which means that row 3 has the maximum value or the maximum coefficient of x1. Which means that I'm going to make that my pivotal equation. Now, just because I don't want to confuse things too much, I'm basically going to take row 3, that's my new pivotal equation because I want to choose the biggest value of the pivot, and I'm going to make it, I'm just going to swap it row 1 because that's where I think the pivotal equation should go. So I'm just going to swap those two rows over just to make it nice and simple. In other words, this is my starting matrix. So I take row 3, so 4, 3, 6 and 13. And I swap it with row 3. So I've still got row 2 in the middle, so 1, 3, 4 and 8. But row 1 and row 3 swap places, so that becomes 2, 2, 2 and 6. Okay, now I start with my Gaussian elimination method. So I do my forward elimination, okay? So remember, this is now my pivot. Okay, so my pivot for x1 is 4. Which means that I can just go through and just do the same thing as before. So let's have a look at row 2. Let's figure out the multiplier. And remember the way which I get the multiplier? I find the element I want to remove. So in other words, the corresponding coefficient of x1, in this case 1. And I want to divide it by the pivot. So in this case, I want to divide it by 4. Okay, so 1 divided by 4, that is the multiplier, which means that in order to get rid of that 1, so the coefficient of x1, I'll take row 2 and take away the multiplier, which is a quarter, lots of my pivotal equation, which is row 1. Okay, so let's do that. So I'll just write it down underneath. So 4, 3, 6, 13. The first row doesn't change. But my second row will become 1, take away a quarter of 4. Well, okay, that's 0. Okay, and remember, always use that as a little check. You want that element to become 0, so if when you do this process you don't get 0 there, you know you've done something wrong. So go back and have a look. Okay, then I move across to the next element. So 3, take away a quarter of 3. Well, 3 take away a quarter of 3 is going to leave me with 9 over 4. Then move across to the next element. So 4, take away a quarter of 6. That's going to leave me with 5 over 2. And moving across the next element, so I have 8 take away a quarter of 13. 8 take away a quarter of 13, that's 19 over 4. Now just pause for a second. You might be looking at this going, hang on a minute, Alex, that is no way that is better than what we're doing with our naive Gaussian elimination. But the only reason why it's not better is because I'm using a fairly contrived example, okay? I deliberately chose this example so naive Gaussian elimination is actually the nicer method to do by hand because it comes out as integers if you do it naive. But what I'm trying to show you is the principle of how partial pivoting works. But just be aware that if you have elements which you end up rounding, in other words, they're non-rational numbers, you can't write them as rational numbers, you need to round them, then it's going to reduce rounding errors in the long run, okay? So just be aware of that. But of course you can stick these numbers in a calculator, right? You're doing a maths degree, I'm sure you'll be fine sticking numbers into a calculator. Okay, fine, then to move on to the next row. So we need to figure out the multiplier for row 3 then. So the multiplier, remember, is taking the element that I want to get rid of, in this case the 2, and I want to divide it by my pivot, in this case it's 4. So in other words, my multiplier for row 3 is going to be a half, which means that I need to take row 3, take away a half lots of the pivotal equation, which is row 1. Okay, so let's do that then. So I'm going to take 2 minus a half of 4. Well, that's going to be 0. Again, that's what I wanted, so I know I'm doing the right thing. Then let's move across. So, okay, let's take 2, take away a half of 3. Well, 2, take away a half of 3. That's going to give me a half. Moving across again, I'm going to have 2 minus a half of 6. That's going to give me negative 1. And moving across the last element, I'm going to have 6 take away a half of 13. So 6 take away a half of 13, that's going to give me a negative half, so negative 1 over 2. Okay, good. So hopefully that makes sense, right? Hopefully that makes sense. So that's the end of step 1. This is the matrix which I've got at the end of step 1. So 4, 3, 6, 13, 0, 9 over 4, 5 over 2, and 19 over 4, and then 0, 1 over 2, negative 1, and negative 1 over 2. Okay, good. So now I just follow exactly the same principle as before. So now I'm going to look for x2, so I'm going to be looking in the second column. However, just be aware, and I did allude to this in the last video, but I will enforce it again now. This first row now is fixed. The reason why we have to leave it fixed is because remember that we're going to be adding and subtracting elements of the first row from the second or third row, okay? So in which case, because I've got these nicely set up as 0, in other words, I've only got one coefficient of my x1, I don't want to go about changing that first row because then I'll end up with numbers where I've got zeros, which is clearly not what I want to happen. So I'm only going to be looking at the second and third row, which means that these are going to be my choices of my pivot. Okay, so let's choose between the maximum of 9 over 4, and of course I'm going to make them absolute value just to make sure, and 1 over 2 absolute value. Okay, well fairly obviously in that case the 9 over 4 is much bigger than the 1 over 2. Okay, so therefore I'm going to keep things the same because I want my pivot to be in the second row, second column. Okay, so I want my pivot to be there, I want my pivot to be 9 over 4, that's the maximum of those things, so I'm going to leave things the same. Okay, don't have to do any swapping. All right, fine. So in which case then, let's go ahead and do this. So let's go for x2. Let's see what we get. So my pivot is 9 over 4. Let's figure out row 3. So we need to do our multiplier first of all. Okay, so my multiplier, remember, I want to get rid of the half. So that's the element I want to get rid of. And I need to divide it by my pivot, so which is 9 over 4. Now if I do the maths, that comes out as 2 over 9. Okay, so that's the multiplier. So in which case I know that to find my new row 3, I need to take my old row 3 and take away 2/9 of my pivotal row, when in this case my pivotal row is the second row. All right, so let's do that. So my first row remains the same, so I'll just write that in. So 4, 3, 6, and 13. Second row will also remain the same because that's my pivotal row, that can't change. And my third row is what's going to change. So let's figure that out now. Okay, so I'm going to take 0 and take away 2/9 of 0. Well, 0 take away 2/9 of 0. Well, hopefully you're happy. That's still 0. Okay, good. I didn't want that to change. Okay, then I move across and I've got 1/2 take away 2/9 of 9 over 4. Well, if I do that, that comes out 0, which is exactly what I wanted. Okay, so that comes out as 0, like so. Okay, so next up I need to take -1 and take away 2/9 of 5 over 2. Okay, so -1 take away 2/9 of 5 over 2. That's going to give me -14 over 9. So just sticking that into calculator. And then finally, -1/2 take away 2/9 of 19 over 4. That comes out as -14 over 9. Cool. So now I've finished the second step of my forward elimination method. Now I can move on to the back substitution method. So you notice the only thing which really changes about partial pivoting is that I have a choice over what my pivot row is going to be. So what my pivot and what my pivotal row is going to be. And I basically choose it such that I want to eliminate the idea of taking a really small or really big numbers, because of course that may lead to errors and rounding errors and things like that. Okay, that's still not spelled right. Back substitution. That's better. Okay, cool. So now I could do my back substitution. So remember, I start with x3. So I can just read off from x3 that third row, because x1 and x2 coefficients are 0, that I have -14 over 9, lots of x3, should be equal to -14 over 9. Well, okay, fairly obviously, x3 has got to be equal to 1. That's good, because that's exactly the same as what I got before. Now let's have a look at x2. So let's go back now. So x2, well, I now know x3, so let's have a look. So my next row will basically give me 0 times x1 plus 9 over 4 times x2 plus 5 over 2 times x3 has got to be equal to 19 over 4. Well, that's good, because I know that x3 has got to be equal to 1, which implies both ways that x3 has got to be equal to 1. In fact, it should just be one way. Okay, so x3 has got to be equal to 1. Let's go back now. Let's use the first row. Now I know x2 and x3 to find what x1 is equal to. So x1 is going to be 4 lots of x1 plus 3 lots of x2 plus 6 lots of x3 has got to be equal to 13. Well, okay, I know that x2 and x3 are both equal to 1. So fairly obviously, x1 has got to be equal to 1. So that should be an x2 there. So there you go. So basically, it's a very, very similar process to what we were doing with naive Gaussian elimination. It's just now you have a choice over what your pivot and pivotal row is going to be. The advantage of doing that is it's going to reduce rounding errors. It's going to reduce the chance of you having to either add or subtract really small numbers or really, really big numbers. Okay?